Welcome, and thank you for joining this webinar, Advancing Quantum Communication, Role, Impact, and Technical Foundations of Quantum Technologies in 6G and Beyond, prepared by Alpert Research Team. Quantum communication is transitioning from academic theory to strategic infrastructure. This webinar explains how physics, not math, can guarantee trust, and how quantum systems integrate realistically into modern communication networks.
Now we have to confront the big strategic challenge, deployment. Moving quantum communication from cutting-edge research to secure, scalable, globally interoperable infrastructure. That requires a focused, collaborative effort.
That coordinated effort really centers on technical standardization. In a field this complex, where components range from fiber links to free space satellites, and protocols range from BB84 to MDIQ-KD, standards are the foundation for ensuring that different systems can reliably and securely communicate with each other. Without standardization, the quantum internet just remains a collection of disconnected labs.
Beyond just making sure a piece of equipment plugs into the network, how do standards specifically help the integration of quantum and classical networks?
Standards provide essential roadmaps for innovation by defining interfaces and protocols. This is crucial for hybrid solutions. How do we ensure the quantum key delivered by a QKD device is seamlessly and securely handed off to a classical cryptographic application? Standardization bodies ensure that integration is secure, promoting innovation while preventing vendor lock-in and proprietary chaos.
Who are the key organizations that are defining these rules globally?
The major international and European bodies are heavily involved. We see active work from the European Telecommunications Standards Institute, ETSI, CEN, CNELEC, and the International Telecommunication Union, ITUT. ETSI has been particularly productive. They've established foundational standards like ETSI GSQKD 022 for network architecture and ETSI GSQKD 023 covering the monitoring interface and data model. The ITUT has also released key recommendations like ITUT Y.3803 for QKD key management interfaces. What are the primary technical and economic barriers that still need to be fully solved before quantum communication really hits mass market deployment in 6G systems?
The economic barriers, as we said, remain the high capital cost of the quantum nodes, though that's on a downward path. But the technical barriers really center on the inherent fragility of quantum states and the limitations of current hardware. A primary barrier is the need to seamlessly integrate hybrid technology. Specifically, the interface between matter qubits, which are necessary for memory and processing in devices like repeaters and flying qubits, the photons used for long-distance transmission.
And that interface is tricky.
It's very prone to loss and error. And because of this, future research really needs to focus on developing increasingly sophisticated machine learning and deep learning algorithms. We need algorithms specifically designed for solving the complex error correction problems in these noisy quantum channels.
So moving beyond conventional error correction to a kind of quantum-aware AI management.
We've already hammered on the distance problem.
It remains the #1 issue. The practical implementation of robust quantum repeaters is the single biggest engineering challenge. Until we solve quantum memory and error correction, QKD is limited to cities and satellites.
And what about the quality of the channel? This idea of decoherence sounds like a constant battle.
Decoherence is the fundamental enemy. It's the unavoidable loss of quantum properties just from the system interacting with its environment. This, plus other environmental noise, means you need very sophisticated quantum error correction codes,
Which have a lot of overhead.
which cuts down on your final key rate. A lot of research is focused on using machine learning to try and discover more efficient error correction paths that give you reliability without killing your throughput.
The economic challenges.
The high cost is a major barrier to scalability, and this is all tied to the limitations of what we call noisy intermediate scale quantum, or NISQ technology. The hardware is complex, it's sensitive, and it's expensive. The real engineering push needs to be toward miniaturized, robust, and cheap photonic integration on a chip. The message is crystal clear. The integration of quantum systems into our network architecture is happening now, not in some distant theoretical future. We've established that quantum communication will not replace classical wireless networks, but it will redefine how trust, security, and optimization are built into 5G advanced and 6G systems.
Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.